So till this day, we talked about all this binary numbers, electronic gates, basic computer analogy, right? Then transistors, IC chips, computer organization, a little bit of 8085 architecture. I know it's difficult, but you have seen that all, how things work between memory to register, how it read-write happens, processor sends a signal, and reading write happens, operating system. And in that registers and RAM, how it works together. And then we switch to operating system process, how operating system allocates memory and processor time, right, with the different algorithms and different types of algorithms, right? That's what we covered in last 4 days. Now, today we'll go to a little bit of history, like a flashback. From where we started actually, right? What is the first mechanical computer or calculator? Someone can tell me. Vinayak or Riddhesh.
So can you repeat?
What is the first mechanical computer or calculator? If you can, what would be the first from your memory? Where it started?
Sir, a machine that calculates.
Your calculator or what?
The calculator.
You remember your calculator. Any other answers from Sheesh? Everybody remembers calculator. It's a bit more modern stuff. Gada, you have a different answer? Okay, so here is a surprise. This is the first mechanical calculator, right? So we started our calculations with our fingers. That's the first mechanical calculator. Manu, we just started the history. Where we started all this calculation, we started with fingers, right? And then somebody would have seen this part. You know this?
Abacus.
Abacus. How many of you don't know abacus? Anyone doesn't know abacus counting? Most of you would have heard about this abacus. What is abacus? How does it work out? Any idea? Counting? It's based on that beats, of course. 1, 2, 3, 2, 10. And there is, anyone knows it? Anyone played with it? Till
Yes, sir.
The Dana knows. What about Gada, Abhirami? Have you done abacus? Manu, have you done abacus? Abacus calculation?
No, we haven't.
No. So let's go to a video, okay? An abacus video. So listen to this carefully, yeah? Can you see my screen?
Yes, sir.
The counting method and the indirect method. The advantages of the counting method are that it's appropriate for children at a young age or with no previous math experience. No math facts or abstract ideas are needed, and the student can start right away. The disadvantages are that it's not as fast as the indirect method, and it's not what the peers are doing in the general education classroom. The advantages of the indirect method are that it's fast once it's mastered, and it is similar to what sighted peers are using, and you can use the same terminology, and it helps understanding the abstract theory of addition and subtraction. But the disadvantages are that you have to memorize your tens facts for addition and subtraction first before you can use it. That can be confusing at first, and it takes a while to learn. A combination of the counting and indirect methods is the best approach. There is a natural progression from counting to indirect as the student develops the understanding of addition and subtraction. I'm here today with Craig, who's volunteered to learn to add and subtract on the abacus. So let's review the basics and counting. Be sure that you know the names. The first thing you need to know, these are the rods. The columns are the rods. We have the 1 beads at the bottom and the 5 beads at the top. This is the counting bar, and when a bead is next to the bar, it counts, and when it's away from the bar, it's the number 0. Okay, so let's start with counting. I'm going to count to 15. Each time I move a bead, it counts as 1. So 1, 2, 3, 4 are moved up against the bar. Remember that when we get to 5, we push it down, and these all at the same time. 5, 6, 7, 8, and 9. And then when we get all of the beads used and we have to go to the next column, the next rod, we move it, but move 9 away at the same time, all one motion. And there's our number 1, 0, 10.
You understood that 10 part, how it reached that 10, that 1 and 0. Can you see that 1 and 0 from this? You understood, right? And now observe now the movement towards 100, how they calculate it, right? Just adding that beads.
Now when we move one more up, we have 11, 1, 1,
1, 1.
12, 13, 14, and when we move the 5, we move it all in one motion, and there's our number 15.
Yeah.
Now let's try counting from 94 to 102. So we'll set the number 94, which we've learned to do, and let's add 1 at a time up to 102. This gives us practice with the 5 bead. So 95 would be all one motion, 96, 97, 98, 99, and now we have no beads left here, so we would add 1, but we have no beads here, so the next number goes over here, and always clear all the 9s in the same motion. And that gives our number 100, 100.
100.
And we could just now
100. That's how 100. And this calculation goes on. So this is how it happens in number counting happens in Abacus. So that is the one of the first mechanical calculator, starting from our hand, and then people also use stones, pebbles, and all that. That's where we started counting calculation. Okay. Now, what is polynomial? It's another calculator. So have you studied polynomial?
It's like an equation with multiple terms, like multiple variables.
Yeah. So from a definition perspective, all right, a polynomial is a function that involves only non-negative integer powers or only positive integer exponents of a variable in equation. Right? So it's equation. It's like quadratic equation, cubic equation. For example, 2x plus 5 is a polynomial, and that has exponent equal to 1. So you have variables and constants. Let's put that way. So what are the examples, real life examples of a polynomial? Why it is used? Why polynomial is used? Where all it is used? Everybody study all this 2x plus 5 quadratic equation in mathematics. But why are we studying? Where is it used? Someone can answer this? Any real life examples? Why are we studying all this 2x plus 5, x squared plus bx plus c and all this? Why are we studying in mathematics? Quick answer. This is actually first calculator, mathematical calculator. Ritesh, Abhirami, any answers? Shreyesh, Dana? So one complex thing I will tell you, a roller coaster, right? An engineer designing a roller coaster would use polynomials, right? Or designing roads, buildings, the structure, they're all polynomials used from a design perspective, right? Everything you see is also a polynomial. You take some recipe also, that there is polynomial. You go to a supermarket, there is polynomial, right? You make pancake 1a plus 1 by 4b plus 1 by 3c, that is polynomial. So making pancake, it's just that you call, some name. But end of the day, everything you see in the, with constants and variables, you go to a supermarket, there is polynomial. You go to, engineers use it from a complex equation point of view, designing roads or curvature and all that. That's all polynomial, practical applications of polynomial. Military, when you shoot a gun with so-and-so features, where it goes, the trajectory of a gun or aeroplane, right, or a rocket, lights of the car, or photo, camera, to which distance it goes, right, where the bullet will hit. That is mathematical formula. So each gun will have probably a mathematical formula, right? So that is also a polynomial, to put it in a scientific terms. But even if you go to a supermarket, you come across that, but I'm just giving different varieties of polynomials. So quadratic equations in standard form, x squared plus bx plus c, we call this. Okay, this is one interesting polynomial, which calculating, and then areas, speed of object, product profit, all that. Everywhere we apply polynomial. Now, let's take one polynomial. This fx is equal to 2x plus 5, right? You can see where x varies 1 to 5 and fx equal to, when x equal to 1, what is fx? Someone can answer this?
So 7.
Okay, how did you get that? 2 into 1 plus 5, right? Agreed?
Yes, sir.
And x equal to 2, fx equal to 2 into 2 plus 5, right? So 9.
Yes, sir.
Agreed. And what is d1? d1 is differential of row number 2 to row number 1 between fx. And what is the differential you get? 9 minus 7. That's the differential right here. Agreed?
Yes, sir.
You agreed? Yeah. And then you reduce 11 minus 9, you get 2. So d1, differential between the immediate rows, is 2. Okay, in this polynomial. You agree with me, right? We are going to interesting stuff. That's why I'm explaining to you. Now I'm taking one more complex one with the power 2. Not complex, it's very easy for you to calculate in mind. What does it become? Let's look at d1. What is d1 in this case? 15 minus 6 is equal to 9. Whereas what is d2? 13 minus 9. In the d1, the differences of d1 shows d2, right? So fx, you get first column, d1 is the differential between fx, d2 is the differential between d1s. And then all the d2s are same, so you don't need to take. So it's 4, 4, 4, 4. Have you observed that? Can you observe, make that observation? So 15 minus 6, 9, 28 minus 15, 13, 45 minus 28, 17. Here, to get d2, 13 minus 9, 4, 17 minus 13, 4, 20, this all, so final differential is all same, so we stop there. Up to 7 we have used here, x is equal to 7 we have calculated, up to 120, the value is 120, total calculation. And then if we take one more, x raised to 7 plus x, I'm saying this for a specific reason. Look at that, fx, if I give 1 raised to 7 plus 1, 1 raised to 7 is 1, right? 1 power 7, what is 1 power 7? 1, plus 1, 2. 1 power, then x equal to 2, 2 power 7. 2 power 7 is 128, plus 2 is equal to 130. Yeah, and it goes on. And differential, this minus this, fx2 minus fx1. So you get here. Here differential, d3 minus d2. Here differential, d2 of the fourth row minus d2 of third row. Like that it goes on. And finally, you will reach a point where everything is same, exactly similar to other tables. Now, why I'm explaining this? This is called differentials, d1 to d7, right? Now, assume that we have all these answers first, right? We get all these calculations. Now, we forget all this 130, 2190. If you put this 128 here, you add 128 plus 2, you get 130. You go this, you put this 9 on top of it. 9 plus 6 is 15, right? If you know 13 here, right? 13 plus 15 is equal to 28. 28 plus 17 is equal to 45. So from an immediate row, you can calculate like this. You get effects that way. So if you know D1, first value, first row, 6, 9, 4. And if you don't know remaining, still you can calculate. If you know the first row, 6, 9, 4, like just by calculation, you set it. You once set it, you can do it by calculation. 9 plus 6 is equal to 15. 9 plus 4 is equal to 13. 13 plus 15 is equal to 28. 13 plus 4 is equal to 17. 28 plus 17 is equal to 45. 17 plus 4 is like that in a reverse way. So initially we did calculate like this way, and the reverse way, if you do it, you get the answers in that order also. This is the principle where Charles Babbage, right, a British mathematician, he invented the first real mechanical computer or calculator using polynomials. So giving a generalization for polynomial, he set this numbers in this mechanical device, and he tried to make a model. He worked on it for 30 years, 30 or 40 years, 30 to 40 years, funded by British government, right? Though it was not commercially used, he worked on it for 30 to 40 years, and I'm going to show you that model.
In the 1820s, the English mathematician Charles Babbage began to design a mechanical device called a difference engine for computing polynomial functions. Babbage's goal was to eliminate all sources of human error in the creation of mathematical tables. The project was funded by the British government for 19 years, but only a small fragment of the machine was actually built. During the period of 1847 through 1849, Babbage drew up plans for an improved device, his difference engine number 2, which had fewer parts yet would calculate more quickly. Difference engine number 2 remained a paper design until the Science Museum in London built the calculating portion of the machine in 1991, and the printer.
Have you listened to that? Actually, this was done in 1820 to 1840, and this was recreated back in 1985 to 1981. It was recreated. Now it is there in San Francisco, I think, some museum, or maybe it's there in London. I don't know, maybe it is shifted to the. So there is one piece. It took again another 16 years, I think, to create model back in 1985. So which was done, initial model was done in 1820s. And then back in 1980s, people worked on it just for a museum piece. So if you go to some museum in London or California, I think maybe Manu knows it, San Francisco, I think there is one museum, it is kept there. This Babbage engine, okay?
In 2002. A second difference engine has also been built and is currently on display at the Computer History Museum in Mountain View, California. A difference engine is not an adding machine in the ordinary sense. It's a special purpose computer that calculates polynomial functions using the method of finite differences. For hundreds of years, computing polynomials was an important problem because polynomials can be used to approximate a wide variety of more complicated mathematical functions, such as sine, cosine, and the natural logarithm. Let us consider the simple first-degree polynomial f of x equals 2 times x plus 5. The value of f at 1 is 7, f at 2 is 9, and f at 3 is 11, f at 4 is 13. Notice that if we take the difference of any two consecutive rows in this table, we always get the same value, in this case, the value 2. A similar thing holds for second-degree polynomials, like f of x equals 2 times x squared plus 3 times x plus 1, except that now we have to compute two columns of differences before we get a constant value. We can use the fact that the second difference column is always a constant to compute consecutive values of f of x using only additions. No multiplication operations are required. To do this, we must first pre-compute the first value in each column. We rearrange our pre-computed values into a new table like this. To fill in the second row, we add the number above each cell with the number above and to the right. And so on, ad infinitum. This method is completely general. For any polynomial of degree n, if you build a similar table with n difference columns, you can compute the next row's values using only n additions. Babbage's difference engine number 2 was designed to evaluate polynomials up to order 7. So a table representing the calculation of a polynomial would have 7 difference columns. For example, this is the table for the polynomial f of x equal x to the 7th power plus x. To compute a sequence of values for this polynomial using the method of finite differences, we would follow the same procedure as before. We pre-compute the first value in each column, then arrange these values into a new table, and start adding. A property of the method of finite differences is that each row can be calculated using only the previous row. You don't need to remember any rows before that. And if you order the calculation sequentially from left to right, you only need a single row of storage in your difference engine. This scheme can form the basis of a simple difference engine consisting of 8 storage registers connected by 7 adders.
This is the mathematics.
Our simple difference.
This mathematics goes on, and let me then now take the actual engine. Okay, and just visit that part also.
A far from finished device by which he intended to revolutionize calculation by mechanizing it. At his soirees, London's intellectual society watched what you see now. As Babbage cranked its handle, this machine produced a series of polynomial calculations that were repeatable and error-free. Most astonishing, it was automatic. Any of his illustrious guests might have operated the handle as well as Charles Babbage, perhaps the geologist Charles Lyell, or Charles Darwin, or Charles Dickens. Once set, the machine seemed able to proceed, to think, on its own. But what was called the beautiful fragment of the machine Babbage had intended to build was all he ever finished of it. In fact, his imagination had already moved on to an even more ambitious mechanism, one that would make obsolete the abandoned machine. The Analytical Engine would be a general-purpose calculating automaton. For most of 30 years, he would revise and improve his notional design. Only a few partial sections of it were built, this one after Babbage's death by his son. The Analytical Engine was an ever-evolving machine. Each breakthrough elegantly drawn up, annotated to describe mechanical motions with a coding system that Babbage claimed was his finest invention. The Analytical Engine may be the most intricate operating mechanism ever fully realized with paper and imagination alone. In 1846, Babbage abruptly changed course. As if determined to make good on an old obligation, he worked for 2 years to complete a full set of drawings for difference engine number 2. It would require 8,000 parts, only a third as many as the first. He offered it to the government, but did not protest when it declined to build it, and the drawings were carefully put away. Eventually, they came from the Babbage estate to rest in the library of the Science Museum in London. Every turn of the engine's driving handle is carried through gears, cams, rods, levers, and springs to release and arrest precisely aligned number wheels. A helical arrangement of steel fingers continually pulls the register towers to find and perform the carrying of tens. In its continuing sweep upward, it is mesmerizing. The intricate printing section can be programmed for 1, 2, or 3 column output, for 2 font sizes at once, for variable margins and column gaps, even word wrap where necessary. It prints hard copy on paper and simultaneously impresses the same output into a tray of plaster to produce a... The printer pauses the entire machine. In the spring of 2008, a clone of DE2 commissioned by Nathan Myhrvold was completed at the Science Museum and shipped to California. At the Computer History Museum, it would charm new thousands of discerning eyes.
What you see is actually something developed later, right, for a museum piece.
So I just wanted to show you how Charles Babbage, as the first, father of computer, what we, from an industry point of view, call him as father of computer, because he was a guy who tried to, make a computer like a complex computer like with the polynomial functions. So the differential part preset in the top, right, and then moving that levers and this, what do you call prefix numbers with teeth that properly add, and then towards left you carry, just like what we did in a table, which I can't show you how it is being done there. That is how it is working. Whatever we have seen in table in a small table with the small numbers, that's being executed or was imaginated in a paper, and actually it was designed in 1985, that particular piece which was showing to you, museum piece. But I think it was not properly physically designed by him. The second one, Analytical Engine. First one he did some work, but second one he didn't continue. His son continued some work. That is how the history is. And then people were confident about that design. And so somewhat in 1985, some mad guys really did that. And for that also people worked for 10, 15 years or 19 years or anything, even in this century, yeah, to make that. So I just posted all these videos from that point of view. And there is also something called a punched card those days. There's a Herman Hollerith video also. You can go through that video later. But this is how that punched card look like, right? And what is this punched card? Again, goes back to 1890s or 1880s, where Herman Hollerith, he was an insurance guy. So when government assigned him a job in the census department, right? So what happens in census? People come to your home and then ask whether you have, how many cars you have, how many rooms you have in your house. So when population goes on, the census takes more number of years, sometimes 10 years, right? In a country with big population. So to reduce that effort, Herman Hollerith tried to do it with this punched card, giving certain notations for this, and you punch it in different places, each having its own meaning. So you punch here, it means the number of rooms is equal to 3, or number of or the house size is like this, or number of people inside a house is so and so. So certain notations like that, yeah. And I think we should go to that video as well now.
Children are in the house, and how many bedrooms do you have, and yada yada, all these different questions, and it was all put on paper, and then all that was taken back, added up together, and then those numbers were put together, and finally they added the whole thing together and came up with the census for the United States. And when we were a small country, not a lot of people, it worked really well that way. The problem.
All these were indicators, like, just like we said, regarding how many people you have in the, or members in the family, right? How many rooms you have in the house, and those indicators. So there are many indicators like this. Yeah.
Was that by 1890, it got to the place where they realized that the time was increasing, and it got to the place where almost the entire year went by. I mean, the entire 9 years went by before they came up with the totals. So they would never catch up. So by 1890, they said, we'll never catch up. So the census said there has to be a better way to do this. And so they put out, said, propose something that's cool that'll solve this problem. I'm sure they didn't use the word cool, but back then they used some other word. But come up with something unique that'll change this, because we can't go on this way, because we'll never catch up, ever. And so that makes the whole thing worthless. And so one of the people who knew the census well and had actually done work at the Census Department was Herman Hollerith. And Herman Hollerith came up with the idea of creating a card with holes in it. And by doing that, he came up with a very novel solution to counting, because that was one of the big issues, is adding up all this stuff. So what he did was he created a device that would punch holes in a card, so a person could now take the census information and punch it in a card, and then the card would be placed in this device here, the handle pulled down, and then wherever there was a hole in the card, it would count up the counter. So all these are counters, and one of those counters might be number of bedrooms. One would be like 1 bedroom, 2 bedroom, 3 bedroom, etc. And how many people would be, on each counter. And so you just pull the handle down, and we do the whole thing at once. Add all those numbers at once. And then it even got more sophisticated, where it had this little sorter unit here. And if they were trying to look for a certain thing, maybe like all the people that had under or over a certain amount of income, the little slot would open up, and they would drop the card in there, so they could actually group.
Okay, so that's the story of punched card, right? Where Herman Hollerith tried to have this is some snapshot of it, okay, to improve this census calculation. And then he used it in insurance, and somehow there was another company, CTR, computer or tabulating recorder, calculated tabulating recorder, company like that. Back in 1911, they combined together, and finally they joined a company called IBM and joined together. And then IBM was from 100 years back, between 1911 to 1925. Earlier the IBM was known as CTR. Then back in 1924, I think they got renamed it as IBM, with a lot of different changes and new products and all that. So, but these days, computer was a business machine. That's why international business machine, IBM, international business machine. Earlier computers were a business machine. It was never a personal computer. Now we are all using a personal computer or tab or mobile phone. But earlier it was a business machine, only for big business purposes. Just like you are seeing in census or big insurance companies, banks and banking companies, all big calculations and all that, right? That is how these things were used, right? And then another invention was this one, vacuum tubes. These were also called diodes. Have you seen vacuum tubes? Anyone have vacuum tube radios, old big radios? Your home, or your father's home, or mother's home, grandparents, grandparents? Have you seen big vacuum radios? I think it was there. It's still 40 years back. We had this, at least a smaller vacuum tube. So it's like thermionic tube with cathode to anode. Electrons flow from one direction. It's a diode. So before transistor, we learned transistor, right? Transistors as building blocks of integrated circuits. So before that, in 1900, early 1900, someone invented. That's John Ambrose Fleming invented diode or vacuum tube. It's a thermionic kind of, it's basically to controlling the electron flow, cathode to anode. So you know cathode and anode, right? Cathode anode. Have you heard that? Cathode anode in your physics or chemistry? So it's basically a diode to control the electron flow or electricity flow. You can think in that way, yeah. And this was used in 1940s ENIAC, one of the first programmable computers. So in 1940s, we reached a programmable computer, but that's size of a room. You can see that in the left side, right? The size is so huge with all these vacuum tubes, and its weight is in tons. Okay, it's in microseconds and 100 kilohertz. That's the speed. But if you look at the weight, it is 30 tons. Used 200 kilowatts of electric power. Consisted of 18,000 vacuum tubes and thousands of resistors and capacitors, inductors, punched cards, card readers, and all that. So this is a huge size. So 1940, we are talking about ENIAC, electronic numeric integrator, something like that. That's in full form, I think. And calculator, numeric integrator and calculator. So if you look at the timelines between 50, 60, 70, if you go run through this, these are some milestones regarding this transistor to electronic punched card, from there to transistor invention to an IBM PC invention, one of the first inventions in 70s, till personal computer, right? 1947 transistor, 1948 with a vacuum tube computer with IBM 604, 49 IBM delivers 604, card program electronic calculator. So these are all some important years in that journey between 47, from a transistor to a PC, 47 to 74, and interim between 50s to 70s. It's a kind of certain milestones in the history. And you can see the computer changing from different types. Earlier it was a room size, and then now this is on top of table. And then 70s, the shift from a business machine to a personal machine. Am I audible, Gada?
You are.
Okay. So here the story, it's somewhat like this. Personal machines start looking like a bit more closer to what we see today. I have seen something like this in 1980s when I first saw the touch one of the computer. It was something like this with some sound, like that. And so again, this was large. So those microprocessors started, and they started getting into people with IBM, Microsoft, Apple, everybody getting into that business. So from punched card, microprocessors started. So every computer used to have this microprocessor, just like I have shown you an 8085 processor. Intel started building chips for that, and then IBM, Intel, Microsoft, everybody started working together to this personal computer, their own personal computer, their own configuration, different configurations started. So that's how it started reaching people. So earlier it was a business machine, and then from 70s onwards, it started reaching people. Yeah, that is one part of the history. Then taking printouts, and then all those kind of things directly from PCs, and then some time sharing systems. Then there is another terminology, mainframe computer. Mainframe computers were huge, again used by business, not by people. So mainframe is a huge computer with huge processing capabilities, not like this. Okay, so that's not shown here. Again, behind the scenes, behind business, people used mainframe computers with the huge processing powers. Okay, all those things got changed. And in 80s and 90s and 2000s, this is something which is even closer to what we see today, right? It's a huge market of microcomputers, laptops we started talking about. Yeah, with more memory, with more processing power, with graphics, with video games, started reaching this. All these is from Wikipedia. So if you go to computer history, you will see this in a with proper chronology. But I just picked it few milestones. right? So if I summarize all those important years, not just this 50 years in this information computer technology revolution, right? 1820, Charles Babbage differential engine was a very important point. 1890, Hermann Hollerith punched card, very important key milestone. 1910 to 1925, CTR and Hermann Hollerith joining to form IBM, right? One of the most important point. Vacuum tube, 1904, key invention, thermionic diode, right? And after that, there is silicon diode as well, but thermionic diode is one of the first one, 1904. One of the important invention. 1945 to 1950, a series of experiments on transistors and later into IC chips by Bell Labs, and continuing 1959 MOSFET, the thing which we explained yesterday as transistor silicon using silicon, that's semiconductor doping and all that we talked about. That is MOSFET, metal on semiconductor, field effect transistor, metal on semiconductor, silicon, right? That is metal on semiconductor. So 1959 was one of the important, because from that revolution was huge, because it started becoming micro, mini, micro, and then from thousands to billions of transistors into this. So these dates or these years, are kind of very important in the whole history. And then 70s and 80s, right? Our Windows and this Apple, Microsoft, iOS, HP, all that personal computers, 80s and 90s. In 90s, we have internet, World Wide Web, yahoo.com and all that. 2000s, mobile phone, Android, iOS, iPhone, tab. This is where we are, right? 2000s, the last 20 years. So this is the full journey of, from, I would say, at least for the last 200 years, especially in terms of computing, right? Starting from Charles Babbage, father of computer. Yeah. And any questions before I move to configuration, or maybe let me close that as well, because it's just 2 slides. Maybe we'll stop after that. So these days, if you go to if you open newspaper, you'll see all this configuration. Gaming, 9th generation Intel Core i5 processor. I'm just picking a name example, right? Intel Core i5 9Z300 2.4 gigahertz, 4.11 gigahertz. So all these, and then 4 core. You know what is the meaning of 4 core? It means there is 4 processors inside. So this is, I think, one example of a gaming computer, not the laptop which probably you are using. Very powerful gaming computer. One configuration, one example of a configuration where you see these days, these are new terminologies, 4 cores. 4 core means 4 processors inside. Okay, memory 8 GB RAM, right? 8 GB RAM, or SD RAM, we call that SD RAM. 1 into 8 GB, sometimes you have 16 GB and 64 GB and all that. So don't worry about these naming, but this keeps changing, right? 8 GB to 64 GB also. You see 1 TB hard disk, 1 TB terabyte, that is terabyte, 1 TB HDD hard disk. That's the meaning of it. And then you have video graphics, certain terminologies for that, right? I don't know what is the expansion for NVIDIA. I will need to look at Google, but it could be some that name of that graphics card, right? NVIDIA GeForce graphics card name. That's a graphic card name, right? I have not used it. And then you have ports. You have USB ports, different USB ports, and all this. And then you have something a bit more simpler one, 10 generation Intel Core i3. I think I am using something similar to this. It's also latest with Windows 10 Intel UHD graphics. For my purpose, I'm using this 4 GB RAM stuff. And then all-in-one desktops, you have that kind of configuration. So if you ask me, which is the best computer to buy one latest for your home purpose, something similar to this. If you use gaming, then you have to specifically ask a configuration suitable for gaming. If you don't have any gaming, you can use something closer to this. And if you buy one, at least use it for next 5 years, right? You can buy, laptop or desktop, thinking in 4 to 5 years of time frame. And if you have games, ask that in a shop specific to gaming computers. That's all I can say, because it's a huge ocean of different configurations. I'm just showing you only one configuration, which is closer to my knowledge, which is Intel and Pentium. There are AMDs and there are other companies, with a different configuration. So you will see all these different names. Some of the names even new to me as well, right? I'll need to browse and I need to search what it means. Okay. But this is how generally, configurations and regarding decision making, which one to buy? People ask me all that, which one to buy? Okay, if you buy something latest, go and buy the latest one. Think of using it for 5 years. That's all I can say. People, which is best one to buy? You want buy one next year, you'll see a better version, right? So with the same, maybe if you spend say $1,000 or $500, again you will see the next year people releasing next versions after versions. You will see that. So you need to fix somehow for your purpose, suitable for your purpose. Okay, I don't have a single answer for this. Clock speeds also, coming faster every 2 years, 3 years. So what is clock speed? So it's in hertz, 2.0 gigahertz, clock cycles per second. You saw that tick, right? Tick, tick. In one of the example, reading and writing from registers to RAM, registers to RAM. There was one video showing that tuck. So it's just a pulse sending, right? A pulse, oscillator sending a pulse. So it's right now, when we talk about 4.0 gigahertz is one by billion. You can see that zeros, 1 0 0 0 0, 9 zeros after that, 9 zeros after 1. 1 by that many part of a second. That is the speed which we are talking about when we say cycles per second, clock speed. Earlier, it was that big computer, it was 200 microseconds, right? 200 microseconds. This is 1 by billionth of a second. That is the kind of speed comparison with 50 years back and today, if you compare the clock speeds. Okay. So these are some kind of comparisons. I think we are done. And for video card and for graphics, there will be different. So as I said, 4-core, 2-core, 3-core are different terminologies used in the market in terms of configuration. And then we have USB ports. It's a universal serial bus. So these days you can see USB 3 is the latest. You can see it blue in color in laptop. So I came to know only recently when I wanted to prepare. I just asked, okay, I need one USB port, but there is something called USB 3 that is the latest. Now, I don't know, yesterday they released something new, but USB 3 is blue in color. That's the latest, right? The external hard drive or external drives we connect these days with this, and you have HDMI, high definition multimedia interfaces, headphone ports, and you can see standard A, standard B, standard C, and all this. Why do we have all these standards in this, in our mobile phone connectors and the USBs? Why do we have the standards? This can be connected in most of the laptops because it has to be standard. Otherwise, you can't use across machines, right? So this is universally agreed standard, right? So if you go to this, more like all companies together agreed on a USB standard, universal serial bus. So from a storage point of view, so they came to certain pins, certain structures. So you can look at this. So there is ABC. So people tell you, if you go to mobile shop, you want C type or B type, because that is a kind of standard, and many companies follow that. So USB 3 is the latest in this case. And in mobile, you will see mini C. Today morning, somebody was asking, okay, you want C type or B type? So that you need to check your own mobiles or laptops, what type it is. Based on that shapes, somehow I look into the shapes and pins and search in net, how many pins it has. Now that it's based on your needs. These are input-output ports, right? These days, even our mouse, your keyboard, everything we connect with USB or storage, all that, right? And sometimes we have bigger storages also connected through USB drives, right? universal serial bus. So it's just that name, universal serial bus. So it's universally agreed, some industry standard, some specifications for cables and certain pins and all that. So everybody can use the same thing, be it a Microsoft machine or be it a Apple machine or HP machine, whichever machine it is. So there is some color standards and all that. And if things change, it's a problem. So you have to continue find that specific one. If you are using older machines. So that's about input output ports, right? And that's it. We actually, finished with all our slides for entire session, right? From a history to configuration. I actually combined history to configuration as one session because configuration, I thought it could be of a 10-15 minutes, so I didn't want to dig on it. So this is where we started, right, with computer. So let me stop here. If there is any specific questions, we can take. So today we covered the history to configuration part, the full connection, right? Where was it? Yeah. So the entire thing, what all things we have covered: computer analogy, binary numbers, electronic gates, transistors, chips, then the entire computer organization, and how operating system manage the processes, right? This memory and all that. And then we went through the history. We saw that Charles Babbage machine. We have gone through punched card. We went through this key milestone dates, and then we finally reached home use, basically from configurations and decision making. So these are things which we covered in last 5 days, and I'm done with actually the full session. Somebody can briefly talk to me in 1 or 2 minutes what all things we have learned. Let me stop and thank you for listening to me. Yeah. Okay. So Manu, you would like to give a 2 minutes summary of everything we have covered?
So what we first covered was basic parts of the computer and how they related to the human body.
Yeah.
And then we learned about binary numbers and then how to relate from normal numbers to binary numbers.
Conversion, yeah. Conversion of decimal numbers into binary numbers. We learned that, yeah.
And then we learned about electronic gates and Boolean commands.
Yeah, Boolean operation.
Yeah, Boolean operations like AND or OR.
Yeah.
And then we learned about transistors and IC chips.
Yeah, and we use transistor gates to build, basically to build electronic gates, right? Using that binary operation. Yeah.
And then we computer organization. In that session, we learned that there are multiple layers to a computer: software, middleware, and hardware, middleware, and software.
Yeah.
Then now we did a history walk, learning about how the computer developed over the years.
Yeah. And also the operating system processes, right? Different algorithms, how things are getting managed, how memory is managed, how processor time is utilized, how processes are allocated to different applications, right? So it's basically we call processes. For your understanding, I'm saying just say applications. So within that there is one more level we call as process, but for your understanding, just keep it as application. So operating system allocates a process, just like with an dosha example. We compared that, and we also said silicon is used inside this, and there is semiconductor properties utilized to make transistors. And then when we went back to history, we also found this bigger vacuum tubes where we started, and vacuum tubes to transistors. That was another journey. And then Charles Babbage machine. So that's all history, right? We started with abacus, Babbage machine, Hermann Hollerith, punched card, from punched card to valve radios. If you haven't seen, if you go back and search in Google, you will see a big radio. I have listened to that big radios, football commentaries using, big radios, and there will be some disturbances and one big antenna outside. I remember that valve radio that we used to call, right? And then that got changed it to silicon diode. So the one was thermionic emission, cathode to anode, control of electron flow, and then it became silicon diode, and then it became transistor. I'm just saying few names. There are many inventions in between, quickly to make you get that history walk. And then we talked about the modern configurations of our laptop and all that. So there we ended. So let me stop here.